Hello, we are back to continue our discussion on electrolysis. This is the part 2 of the episode on electrolysis, and we will talk about the quantitative changes during electrolysis. Last time, we predict the product at the electrode in an electrolytic cell, given the condition, if, if it's a molten state or the aqueous solution, that will affect greatly the reactant or the product rather in the respective electrode. Faraday, from his series of experiments, arrived at a quantitative relationship between the amount of chemical changes during electrolysis and the quantity of current used and the length of time the process is being run. In his first law of Faraday, he stated that the mass of the chemical substances produced at the electrode, meaning the anode and the cathode, is directly proportional to the electricity that passes through the solution. Therefore, we can write that the mass produced at the electrode is proportional to the amount of electricity passes, where Q is the quantity of electricity in the unit coulomb. In mathematics, we can remove the proportionality sign by replacing that by an equal sign and a constant, where K is the proportionality constant. Again, Q is the quantity of electricity. Since Q in your physics is an expression of the amount of current or current times the time, therefore we can replace the Q expression by I times T, where I is the current in the unit ampere and T is the time expressed in the unit second S. And 1 coulomb is 1 ampere second. So, the first law can be expressed as the mass produced at the electrode, whether anode or cathode. In the last episode, we predict the product at the cathode and the anode respectively based on the type of electrolyte that is used in the electrolytic cell. Okay, proportional to the amount of electricity. Again, the K is the proportionality sign. Okay, and we can replace the Q by the expression I times T. Okay, we note them as equation 1 and equation 1 prime respectively. Okay, furthermore, Faraday make a series of different electrolyte, okay, composed of different substances, but the salt of the same anion. In the first electrolytic bath, that he connected to a series of 4, say example 4, and he passes 1 Faraday an amount of current through. This is a series, so the amount of current passing each bath is the same. Okay. So he found out that the masses of the different substances produced by the same quantity of electricity are proportional to their equivalent masses. So, in the first electrolytic bath, we have the electrolyte is silver chloride. So, we have silver ion and the chloride ion. Here, we have copric chloride, we have copper ion, and the chloride ion. In the third, we have auric chloride. So, we have gold positive 3 by the crisscross method and the chloride ion. And in this, you have a molten manganese chloride. It is important that it's molten because that will affect the product. These 3 metals are below in activity with respect to your hydrogen in the activity series. So, it could be an aqueous. Okay, we have here mercury, silver, copper, and gold. So, if water is present, the hydrogen will not be deposited at the cathode. It is the metal because there are metal silver, copper, and gold because they are below in activity with respect to the reference metal, which is hydrogen. And magnesium is above hydrogen. So if this is an aqueous solution of magnesium chloride, okay, it is the hydrogen that will be deposited at the cathode. So since it's molten, no hydrogen ion from the oxidation of water. So we have the manganese positive, magnesium rather ion positive 2, and the chloride ion. So from our previous knowledge, in the part 1 of electrolysis, the positively charged would migrate to the negatively charged, and you have that one. Okay, and you have that one. Okay, sorry. And this one. And you have the negatively charged attracted to the positively charged. Since we have chloride as the anion, in the anode we have chlorine gases here. In these three, you have aqueous solution, meaning water is present, so oxygen is also deposited here. So you have hydrogen here and the negative ion of oxygen from the water. Okay. Okay, here no, it's molten. So the chloride and oxide producing oxygen gas and chlorine gas at the anode. We found out that this is when 1 mole of electron or equal to 1 Faraday, the amount of metal deposited at the cathode is equal to the equivalent mass of the element. Then a current of 1 Faraday will cause the oxidation or reduction of 1 equivalent mass of the substances. Okay. If we consider the following cathode reaction for the first electrolytic bath, where silver chloride is the electrolyte, the reaction that takes place here is that 1 silver ion, at the cathode you have silver ion, plus 1 electron would give you silver solid. Okay. On the second, we have the copper ion, positive 2, plus 2 electron would give you copper solid. Here, gold, positive 3, plus 3 electron would give you gold solid. Here we have positive 2 plus 2 electron would give you magnesium solid. Okay, so that means that 1 mole electron, which is 6.02 times 10 to the 23rd, deposit 1 mole of silver. In the second electrolytic bath at the cathode, 2 moles electron deposit on 1 mole of copper, which is 64 gram. Okay. When we say 2 moles of electron, that is, you multiply this by 2, so it is 12.04 times 10 to the 23rd. Produce 64 gram of copper. Or to simplify, 1 mole of electron, you divide that, will deposit 1/2 mole of copper. And in the third electrolytic bath, 3 moles electron deposit 1 mole of gold. And gold from your periodic table is an atomic mass of 197 gram. Or to simplify, if you have 1 mole of electron, that will produce only 1/3 mole of gold. Okay, if you divide that by 3, so that would be 1/3 mole of gold. Okay, so 1 mole of electron will satisfy only 1/3 of an atom or ion of gold. Sorry. Then for the fourth electrolytic bath, 2 moles will produce 1 mole. Okay, 2 moles will produce 1 mole of magnesium, and the atomic mass of magnesium is 24 gram. Or 1 mole of electron will deposit 1/2 mole of magnesium to divide. So Faraday says when 2 or more different metals are deposited, this is one of his findings. by the same amount of electricity at the same time, more of the metal with higher equivalent mass will be deposited. With the same amount of electricity and with the same time, so more in this case of the poor electrolytic bath, more silver will be deposited because the equivalent mass of silver is 108 gram per equivalent compared with that of copper, which is 32 gram per equivalent, gold 65.67 gram per equivalent, and magnesium 12 gram per equivalent, where equivalent mass is an expression, is molar mass over N, where N is the number of electrons gained or lost, and that is the molar mass. That is how this value is obtained. Okay, from the reaction, the atomic mass or molar mass of silver is 108 gram per mole, and there is 1 electron involved to reduce silver ion to silver metal. Okay, so it is over 1, so it is 108. For copper, the atomic mass or molar mass is 64 gram, and there are 2 electrons gained by cupric ion to be reduced to copper metal. So 64 divided by 2, that gives you 32 gram per equivalent. And for gold, there are 3 electrons that is gained by auric ion, and the molar mass is 197 gram. We divide that by 3, and that is 197 over 3, that is 65.67 gram per mole. And for magnesium, you have 24 gram per mole, divided by 2, equivalent per mole. 2 electron per mole is needed to deposit 1 mole of magnesium. So 24 divided by 2, we have 12 gram per equivalent. Okay. So from this relationship, from these findings of Faraday, for his second law, he states that the equivalent mass is proportionate to the amount of Faraday that will pass. Okay, again, in mathematics, we can remove the proportionality sign by replacing it with an equal sign and a factor of k, which is the proportionality constant. And we solve for your k, it is equivalent mass over F, the Faraday constant. Okay, we name that expression for k as equation 2. If we substitute this equation 2 to the first law of Faraday, here, if we substitute equation 2, the expression for k, to equation 1, based on the findings of Faraday on his experiment on a single electrolytic cell. Okay, and he states that the mass of a chemical substance produced at the electrode for anode and cathode is directly proportional to the electricity that passes through the solution. Then for his second law, he constructed a series of electrolytic cells. And he found out that the equivalent mass deposited at each cathode of the electrolytic cell that is series is proportionate to the amount of Faraday that passes through the series of electrolytic bath. So we solve for that k and substitute to this equation. We can therefore combine the two laws or observation of Faraday. Therefore, the mass produced at the electrode, whether it's cathode or anode, is equal to the equivalent mass of the substance that is produced at the cathode or the anode respectively over the F value, which is the Faraday constant, and the quantity of current passing through. Or we can express the Q as I times T. Q here is the quantity of electricity. This is not the chemical equilibrium constant. Okay. So we can have the two expressions in terms of quantity of electricity or current times time. Again, from your general chemistry knowledge, the expression for equivalent mass is molar mass over N, and the unit is gram per equivalent, where mm is the molar mass of the substance deposited at the electrode. And that is either anode or cathode based on the principle that we have learned in the predicting the product of electrode on the first episode of electrolysis. Again, the N is the number of electron gain if it is in the cathode, or loss if it is in the anode. And 1 mole electron is equivalent to 1 Faraday, and it is 6.02 times 10 to the positive 23 electron per Faraday. And the Faraday constant has a value of 96,500 coulomb per equivalent. Okay. In the past discussion, the value of Faraday is joule per volt, which is the expression for coulomb. Okay, let us have an application on the use of this Faraday equation to quantify the product at the anode and at the cathode. Okay, for the first application of the Faraday law, we are given a steady current of 3 ampere is maintained for 10 minutes in a silver nitrate solution. You were asked how much silver is deposited at the cathode. Okay, since we have a silver nitrate solution, that means water is present. We have the silver nitrate will ionize to silver ion and the nitrate ion. Okay, that is applying your knowledge in dissociation in your senior high. Okay, so in the electrolytic bath, there would be silver ion and the nitrate ion. And water is present as well. Okay, so you were asked how many grams or how much silver is deposited at the cathode. So silver will be deposited here. So the reaction is the silver ion in the aqueous solution will gain 1 electron to be reduced to silver solid. And the current is given 3 ampere and the time is 10 minutes. So the time of 10 minutes is converted to second. So for every 1 minute, you have 60 seconds. And that gives you 600 seconds. Okay. Your I is 3 ampere. So required is the mass of the silver deposited at the cathode. If what is asked is the mass of silver deposited at the anode, then your answer is none, because silver has to undergo reduction and it must be at the cathode. The reduction will never take place at the anode. Okay. Since the phrasing of the question is correct, so we move on to the computation. What is the mass of silver at the cathode? Okay, the F is constant, the I is given, time is given, and we compute for the equivalent mass of silver. And this is based on the balance equation. So the equivalent mass of silver is the molar mass of silver over N. So from your periodic table, silver has an atomic mass of 108 gram per mole. Okay, and the number of electrons that is gained per mole of silver is 1. Okay, equivalent per mole. So the mole. Okay, so that gives you the equivalent mass of silver is 108 gram per equivalent. So we have that. So we just substitute. So the mass of silver produced at cathode is, we just plug in the value 108 gram per equivalent times the I, we have 3 ampere, times the time, 600 seconds, over the Faraday constant, 96,500 coulomb per equivalent. The unit equivalent cancel out. Ampere second is coulomb. Okay, so the mass of silver produced at cathode 96,500, and that gives you 2.01 gram silver. Okay. You must complete your answer with the proper unit and identify what is it. Okay, what is asked is the mass. Okay, moving on to the second example. We are given here how long will it take to deposit 1.5 gram of copper on a metal when a current of 5 ampere is applied to cupric sulfate solution. So we have here a cupric solution. Okay. So what is given is the mass of copper. Okay, so in this case, we have copper ion and the sulfate ion, -2. So the copper will be deposited at the cathode, and it is given as 1.5 gram copper metal. And the current is given 5 ampere. So from the reaction at the cathode, we have copper ion plus 2 electron will give you copper solid. Okay. Even if it will have water, it's the copper that will be deposited. And the required is the time, how long. So the unit is not specified. You can decide later whether it will be expressed in minute, hour, or what. But what you can derive from the equation of Faraday, T is in unit second. Okay, so the mass is given, the mass of copper at the cathode. The F is a constant, I is given, the time is the unknown. We can solve the equivalent mass. Okay, from the expression, equivalent mass of copper is the molar mass of copper over N. From the balance equation, the N is 2. So from your periodic table, the atomic mass of copper is 64 gram per mole. And there are 2 equivalent per mole. The mole cancel out. So the equivalent mass of copper is 32 gram per equivalent. So manipulating the equation, we can solve for the time. Okay, and that is in the unit second. So T would be equal to the F value times the mass of copper over the equivalent mass of copper times the current. So we substitute where F is 96,500 coulomb per equivalent. and the mass is given 1.5 gram copper. The equivalent mass is 32 gram per equivalent, and the value for I is 5 ampere. The gram copper will cancel out, equivalent will cancel out. Since 1 coulomb is 1 ampere second. So the ampere with ampere there, leaving you the unit second for the coulomb. Okay, so you have 96,500 times 1.5 over 32 times 5, the unit second. So the time is 904.69 seconds. You can express that in minute. You have 60 seconds is 1 minute. If it's asked in minute, that will give you 15.08 minutes. So it takes you 15 minutes to flake out 1.5 gram of copper with a current of 5 ampere. Okay. Now next number, we're given a current strength in ampere is required to deposit 500 milligram of nickel from a nickel passive to plating cell for an hour. Okay. So what current strength in ampere? So I is being asked, the current in ampere. To deposit, so that is the mass of nickel, which is 500 milligram. Okay, and the time is 1 hour. So you express that in second. In 1 hour, you have 3,600 seconds. So your time is 3,600 seconds. Okay, so you have a nickel positive 2 in a plating cell. So the reaction is the nickel ion plus 2 electrode will give you the nickel solid. This is in the aqueous solution. Okay, so the nickel ion here will be deposited at the cathode. Okay, the mass of the electrode at the cathode is given. This is constant. The time is given, and you are asked for the I, or the current. EM, or the equivalent mass of nickel, can be solved. Again, equivalent mass of nickel would be the molar mass of nickel over 2, okay, which is the equivalent per mole. That is equivalent per mole. Okay, from your table, periodic table, the atomic mass of nickel is 58.7 gram per mole, and over 2 equivalent per mole. The mole cancel out. So the equivalent mass of nickel is 29.35 gram per equivalent. So we have the value, and we solve for your I. Again, you have the I is equal to F value, mass of nickel, just substitute here, okay, over time. So we plug in the values. We have 96,500 coulomb per equivalent, and the mass is given 500 milligram, and the time is 3,600 seconds, and 1 gram is 1,000 milligram. So milligram cancel out. We miss the equivalent mass. Okay. So we have here the equivalent mass 29.35 gram per equivalent. The equivalent cancel out, the gram cancel out. That will give you 0.46 ampere, because coulomb second, since 1 coulomb is 1 ampere second. So the second here will cancel out with that one, leaving you the unit in ampere. So this is the strength of the current that must be flowing in this type of electrolytic cell to plate out 500 milligram of nickel for a period of 1 hour. Okay, for the fourth number, we have how many coulomb will it take to plate out 11.2 gram of iron from a solution of ferrous chloride. Okay, let us have it by the crisscross. We have ferrous chloride. Chloride is very soluble in water, so it will ionize to ferrous and chloride ion, 2 moles. So the ferrous is present and the chloride ion. Okay, so this must be a molten state, no water, because iron is above hydrogen. So iron will not be deposited if water is present. Okay. So what is asked is the Q. And you are given the mass of iron, which is 11.2 gram iron. How many coulomb? So Q is being asked. So we can use the equation 3 of the Faraday equation here. This Q is being asked. Okay, to continue, this is given. That is a constant that is being asked. So we can compute for the equivalent mass of iron. It is the molar mass of iron over N. And for that reaction, you have iron, positive 2, must gain 2 electrons to be reduced to iron, from ferrous to iron metal. So your molar mass of iron is 55.8, so let us have 56 gram per mole. And you have 2 equivalent per mole here. That will cancel out. So the equivalent mass of iron is, you have 28 gram per equivalent. So then we have that one. We solve for your Q. Your Q is Faraday times the mass of iron over the equivalent mass. So we substitute 96,500 coulomb per equivalent times the mass given 11.2 gram iron over the equivalent mass 28 gram per equivalent. The equivalent cancel out, the gram cancel out, leaving you the unit in coulomb, which is the required unit. We have 38,600 coulomb is needed to deposit 11.2 gram of iron. Okay, for the PIP example, in a nickel sulfate bath, a current of 12 ampere is employed to plate nickel on both sides of the cathode, which is a square metal sheet that is 5 cm on each side. The density of the metal, you're referring to the nickel, is 10.5 gram per cubic centimeter. Now you are asked how much nickel is plated at the cathode in 1 hour. And letter B, what is the thickness of the plating on the cathode? Okay, the required for letter A is the mass of the nickel deposit at the cathode. Okay, why at the cathode? Because the nickel is a cation positive, so it will be deposited at the cathode. And the thickness of plating. So the current is given 12 ampere. And the time of plating is given 1 hour. So in 1 hour, you have 3,600 seconds. So that is equivalent to 3,600 seconds. Then you are given the density of nickel, which is 10.5 gram per cubic centimeter. And the metal to be plated out has a measurement here that is 5 centimeter from each side. Okay, so if we enlarge it here, we have this the square metal to be plated, that is 5 centimeter. Okay. So to begin with the mass of nickel deposited at the cathode, we use the Faraday equation that we derived a while ago. Okay, this is being unknown as the mass of the nickel is a constant, dye is given, time is given, so we can solve for the equivalent mass. From the statement, nickel sulfate bath. So the nickel sulfate bath would mean that sulfate is very soluble in water, therefore it will ionize to nickel ion positive 2 and the sulfate ion. Okay, from the crisscross method, that is positive 2. Okay, see the oxidation state of the metal is very important. So you must have gain the skill in determining the oxidation state. Okay, so the reaction would be nickel ion here. You have nickel that will plate out. Okay, it is the nickel that will plate out the metal 5 by 5 centimeter plus 2 electron to plate out the nickel metal. Okay, 2 because oxidation number is positive, 2 plus negative 2 is 0 at an elemental state. Okay, so we have that one. We can solve for the mass that is being asked for letter A. So therefore, mass of nickel deposited at cathode will be equal to, we substitute the given We solve first the equivalent mass of nickel in your periodic table. Again, it is 58.7 gram per mole, and the N is 2 equivalent per mole. That will cancel out, and that will give you 29.35 gram per equivalent. So we have 29.35 gram per equivalent times the current 12 ampere, and the time is 3,600 seconds. And the Faraday constant is 96,500 coulombs per equivalent. So the unit coulomb with ampere second will cancel out. Equivalent cancel out. That will give you mass of nickel deposited at cathode is equal to 14 gram nickel. Okay, we have now answered for letter A. To continue for part B, where we are asked for the thickness of plating. Okay, we are given the mass. We have computed the mass of the plating of nickel, and we're given the density. Okay, from that we can compute the volume of plating. Since we define density is mass per unit volume, so volume is mass over density. Okay, so the volume of plating is equal to the mass 13.14 gram nickel over the density, which is given as 10.5 gram per cubic centimeter. Okay, and that will give us the value 1.25, and the unit is cubic centimeter because the gram cancel out, and the final unit is cubic centimeter. Okay, why do we have to compute the volume of plating? Because we're asked for the thickness of plating. Since we have the surface of the metal to be plated is a square that measures 5 centimeter by 5 centimeter on each side. And if we draw if we have that is your 5 centimeter by 5 centimeter. So assuming the plating will take place here, the surface, and you have that one. Okay. Okay, or if we take, that is the top view. If we take the cross-sectional view, that would be that one. And the plating would be, okay. That is the cross-sectional view. You have here the thickness is, if you let x the thickness of plating, which is being asked for letter B. Okay. So that is x and that is x. So we have here 2x. Okay. Assuming that the thickness of the metal to be plated is negligible. Okay. So since that is 5 centimeter, so the total length here is 5 plus 2x. Okay. For the cross-sectional. In this case, since the thickness is x, okay, so this is 5 plus 2x. Likewise, this side would be 5 plus 2x. So if we take the isometric view, that is the metal. Okay, so this thickness is 2x, x on both sides, and this one is 5 plus 2x, and this is 5 plus 2x as well. Okay. So, using your knowledge in solid jaw or simply your algebra, okay, since the metal plate to be plated will be plated on both sides of the cathode, okay, the upper and the lower, neglecting the thickness of the metal, just the side, the measurement of each side being 5 centimeter. So the volume from your knowledge in solid jaw or even in algebra or simple geometry, okay, you have the formula volume is the cross-sectional area times the thickness. And since we have a square here, the cross-sectional area is a square. Okay, so the volume is the side square, the measurement of each side times the thickness, okay, which is equivalent to 2x. Okay, so if we have an S, the measurement of the side is 5 plus 2x square, and the height, which is 2x, that would be the volume of plating. This would give you a third-degree equation. So, assuming you make a valid assumption that x is very small. So, you make a valid assumption, assume that x is very thin. Hence, 2x is approaching 0. But you cannot substitute that there. Therefore, volume of plating would be equal to 5 square times 2x, where 5 is the measurement of the side of the material to be plated, the given 5 centimeter. So that is that is centimeter. 25 centimeter times 2x. And the volume is 1.25 centimeter cube. So we solve for x. This is 25 square. 0.025 centimeter. Okay. Or that is around 0.25 millimeter. So very thin. So the assumption that x is very thin is valid. Okay. So this is the thickness of plating. For the sixth problem, we're asked to consider only the cost of electricity. Would it be cheaper to produce a ton of sodium or a ton of aluminum by electrolysis? So you are given here the mass of sodium and the mass of aluminum to be equal. And you are asked which is cheaper to produce by electrolysis. So banking on the equation of Faraday that the mass produced at electrode is equal to equivalent mass over F times Q. So from this equation, that the mass of sodium and the mass of aluminum is equal, we can therefore say that the equivalent mass over F Q for sodium is equal to the equivalent mass over the F and Q for aluminum. Okay. Since F is a constant, we can cancel that one. Okay. So we can compare that the equivalent mass of sodium times the Q required for sodium is equal to the equivalent mass of aluminum times the quantity of electricity required to deposit a ton of aluminum. So we can solve for the equivalent mass of sodium. Okay, since sodium, you know that sodium is family 1A plus 1 electron would give you the sodium metal. So 1 electron is involved. So from your periodic table, the atomic mass of sodium is 23 gram per mole. And you have 1 electron or 1 equivalent per mole. So the equivalent mass of sodium is 23 gram per equivalent. Now for aluminum, it is family 3A, so it's the 3 electron to be reduced to aluminum. So this is the reaction at the cathode when aluminum has to be deposited during electrolysis. And this is the reaction at the cathode when sodium is to be deposited by the electrolysis. Okay, so the equivalent mass of aluminum would be equal to the atomic mass of aluminum is 27. You have 27 gram per mole from your periodic table over 3 equivalent per mole. So the equivalent mass of aluminum is 9 gram per equivalent. Okay, so if we substitute it here, the equivalent mass of sodium is 23 gram per equivalent. Okay, you have the Q of sodium. The equivalent mass of aluminum is 9 gram per equivalent times the quantity of electricity needed to plate out the aluminum. The unit gram equivalent will cancel out. So if you solve for the Q for sodium in terms of the quantity of electricity in terms of coulomb for to flake out aluminum. You have 9 divided by 23. You have 0.39 Q of aluminum. So what is meant by that? Or you can restate that as the Q of aluminum is 2.56 the amount of electricity needed to deposit sodium. That is another way of stating that. So that means what? Sodium will require only almost 40% of the electricity needed to flake out 1 ton of aluminum. Or aluminum will require 2.56 times the quantity of electricity needed to plate out 1 ton of sodium. So which is cheaper from that? Therefore, sodium is cheaper to produce than aluminum by electrolysis. Why so? Because given the same quantity of electricity, only 9 grams per equivalent of aluminum will be plated out, and 23 grams of aluminum of sodium will be plated out given the same time and the same quantity. So therefore, sodium is cheaper because it will require only 40% of the quantity of electricity that is needed to plate out 1 ton of aluminum or any mass, given the same mass, whatever unit of mass is required in plating out these two metals. Okay. For the last example problem, we are given an aqueous solution of sodium iodide is placed in a beaker with 2 inert electrodes. When the cell is attached to an external battery, electrolysis occurs. You are asked to write the half reaction occurring at the anode and what is its sign. And letter B, you are asked what is the half reaction occurring at the cathode and what is the sign. And if you are given 0.05 ampere that flows through the cell for 5 hours, how many grams of each product are formed? And if the battery operates at 6.0 volt, calculate the number of kilowatt hour of energy expended in part C. Okay, having this equivalent that 1 kilowatt hour is 3.6 times 10 to the 6 joule, and 1 joule is 1 coulomb volt. Okay. Now, for a given, okay, we have here the pre-body diagram for an electrolytic cell that is composed of an aqueous, okay, sodium iodide, then aqueous. So, the sodium ion and iodide ion is present in aqueous solution. Okay, so meaning the sodium iodide is dissolved in water, so it will ionize to sodium ion and iodide ion. So we have the sodium ion, iodide ion, and the word aqueous meaning there is water and oxygen. Okay. So from our previous knowledge that at the anode oxidation reaction, so from our discussion on predicting the electrode product at the anode, for letter A, we can have the anode reaction. Okay, since water is present and iodide is present as well, the anode reaction, and the word aqueous, water is present, so 2 moles of water will oxidize, and the anode oxidation reaction will take place to 1 mole of oxygen, 4 ions of hydrogen, and giving 4 electrons. Okay. And the iodide ion as well. Okay. You have the iodide ion for 2 ions of that, forming 1 mole of iodine gas and 2 electrons. And of course, the sign of the anode here is positive. Okay, so these are the reaction at the anode since we have an aqueous solution. Both oxygen from the oxidation of water and the iodine from the iodide being highlighted will become an halogen. Okay, so for letter B, you are asked for the cathode. So for your cathode reaction, sodium is present and it is an aqueous solution. Okay, again, referring to your activity series, sodium here is above hydrogen, so it is a greater tendency to donate electron or to lose electron than to gain electron with respect to hydrogen. So sodium will not be deposited at the cathode. Instead, it is the hydrogen gas from water. Okay, so from that you will have the hydrogen ion 2 plus 2 electron will give you hydrogen gas. But there would be 6 or 3 moles of hydrogen gas. But for each mole of hydrogen gas, only 2 moles is involved. Okay, so this is for letter B, and the sign of the cathode is negative. Okay, now for your letter C, you are given the current 0.05 ampere and the time is 5.0 hours. You convert that to second. Okay, so that would be equal to 5 times 3,600 seconds per hour, 18,000 seconds. Remember, the time should be expressed in second. Okay, for part C, we use the Faraday equation. Remember the Faraday equation. Okay, you are asked how many grams of each product are formed. So you are asked this one. How many grams? So for letter C, you have the mass produced at electrode is equal to the equivalent mass times the current times the time over the Faraday constant. Okay, this is for part C. So to compute for the mass here at the anode, how many grams of each product are formed? So your product is oxygen, iodine at the anode, and hydrogen at the cathode. So we determine the equivalent mass of each. Okay. So, the equivalent mass of oxygen. The molar mass of oxygen is 32 gram per mole because the atomic mass is 16 gram per atom. So we have 32 gram per mole because oxygen is a diatomic element. And for the reaction involved, you have 4 electrons. Okay, here. That is loss per mole. Okay. So you have 4 electrons or equivalent per mole. The mole cancel out. That will give you 8 gram per equivalent for oxygen. Say for the equivalent mass of iodine. Again, iodine is a diatomic. The atomic mass of iodine is 127 times 2. Okay, diatomic. Okay, so you have 127 times 2. That is 254 gram per mole. Being diatomic, there are 2 atoms per mole. And for the reaction, it loses 2 electrons per mole. So the mole cancel out and that will give you 127 gram per equivalent for iodine. Okay, for hydrogen at the cathode, we continue here. For the equivalent mass of hydrogen, the molar mass, remember the equivalent mass is molar mass over N. Okay. So here, the molar mass of hydrogen is 2 gram per mole because the atomic mass of hydrogen is 1 gram per atom and there are 2 atoms per mole. And the number of electrons involved per mole is 2. But if the total number of hydrogen that will satisfy by the 6, you have 6 here and 6 electrons and 3 moles. So 3 divided by 6 is 2, still 2. Okay? So the mole that will give you 1 gram per equivalent. Okay. So next step is we compute the mass of each at the anode here. At the anode electrode, okay, A, the mass of oxygen produced is equal to the equivalent mass of oxygen is 8 gram per equivalent. The current is 0.05 ampere and the time is 18,000 seconds. And the Faraday constant is 16,500 coulomb per equivalent. Equivalent cancel out, coulomb and ampere cancel out. Therefore, the mass of oxygen produced is okay. For letter B, the mass of iodine at the anode produced or plated out. Okay, the equivalent mass of iodine is 127 gram per equivalent. Again, the I is 0.05 ampere and the time is 18,000 seconds. And the Faraday constant, 96,500 coulomb per equivalent. Okay, the equivalent cancel out, coulomb, ampere cancel out. That will give you the unit gram of iodine. This will give you 1.18 gram iodine gas. Okay, at the cathode, electrode. Okay, mass of hydrogen gas produced. Again, we have the equation. Equivalent mass of hydrogen is 1 gram per equivalent hydrogen times the I, 0.5 ampere, and the time, 18,000 seconds, over the Faraday constant, 96,500 coulomb per equivalent. Equivalent cancel out, ampere second cancel out. That will give you the mass of hydrogen produced. You have 9.33 times 10 to the negative 3 gram hydrogen gas. So for letter D, we're asked to calculate the number of kilowatt hour of energy expended in letter C, where the I is given. Okay, for letter C, the I is given as 0.05 ampere, and the time 5 hours, which is equivalent to 18,000. Ampere second is coulomb, and we have the conversion here. We're given the conversion that 1 joule is 1 coulomb volt, and 1 kilowatt hour is 3.6 times 10 to the 6 joule. So we can convert the energy is equal to the current times the time and the voltage power, okay, which is the unit in volt. Okay, so we have 0.05 ampere times 18,000 second times 6.0 volt, and that will give you 5,400, the unit ampere second volt, and that gives you 5,400 coulomb volt. That is the energy that is, and the unit is in kilowatt hour that is being required. Okay, since 1 joule is 1 coulomb volt, and you have 3.6 times 10 to the 6 joule is 1 kilowatt hour. So the energy expended in part C, given the current 0.05 ampere and a time of 18,000 ampere and a power, the operating power of the voltage rather of the battery is 6 volt. So you have 1.5 times 10 to the negative 3 kilowatt hour, or that is 0.0015 kilowatt hour. Okay, Okay, that ends our discussion on the application of Faraday law in quantitative determination of the product during electrolysis. Okay, that's all for electrochemistry, and see you in the future videos in chemistry. Till then, bye and have a good day.